Okay, I think we can start the afternoon session. We will continue with neutrinos with Andrade Gouvea. Okay, I have an announcement, but I'll do it later.
Okay. Let's just adjust this. Yeah, the glasses don't help. Okay, it's fine. Okay, so this is where we stopped. So I told you that the basically I want to get to 2001 relatively quickly, and the pion was introduced because the pion, first of all, had all this big story about the fact that the pion was confused with the muon for about a decade or so. But there's another problem associated with the pion that I'll come to in just a second. And but the first thing I want to talk about is how is a neutrino actually observed experimentally. This is one of these discussions that are not useful about, what does it mean for the particle to be discovered experimentally. And you can argue that when Pauli postulated that the neutrino exists, the neutrino was discovered because the assumptions he made were relatively benign. So he assumed energy momentum conservation, and then he could even predict what some of the properties of the particles were supposed to be just by measuring, if you want, the rest of the event. So the neutrino is never measured, but everything else about the event is measured, and then you can use energy momentum conservation to predict or to determine what the properties of the particle are. When people talk about discovering the neutrino, what they're really talking about is that they would like to see the neutrino hit something and give you a non-trivial effect. So you don't just want to have a passive effect of the neutrino being produced, but you'd like to be able to produce one and then have this radiation, if you want to think about it that way, propagate and then lead to some observable effect somewhere else. So that's what discovering the neutrino means. And I told you that the first component to this discovery was the Fermi Theory, which allowed you to calculate what the cross-section was for what are the physics processes you can look for detecting a neutrino. And the challenge for that particular case was that the cross-section was really small. I don't remember the numbers, like 10 to the minus 40, but it's really small, it doesn't matter, or centimeter square, but it's a very small number. And there was no way that in the 1930s people could envision doing an experiment where you could actually measure something that made sense. And like I said before the break, the really big event that changed everything really was the Second World War. And the really big event was the invention of nuclear reactors. So nuclear reactors are just a place. So if you don't care about nuclear reactors at all, the thing that we care about the most is that nuclear reactors are a place where you get a lot of elements that decay via beta decay, and you put them in one place. A lot of it. So people did a lot of engineering to do this. So they take a lot of stuff that will undergo beta decay. They collect it in a very, very dense environment. And then they even make the whole thing enter fission. So you produce all of these really weird elements that you never see anywhere in the real world. But all of these things decay via beta decay very efficiently. And then you get a lot of neutrinos that way. So nuclear reactors are the thing that changed everything, because it turned out that now you had a really intense source of neutrinos. So the cross-section didn't change, because you can't change that. But you ended up getting a very, very large flux of neutrinos. Now, as you know, nuclear reactors were not invented to generate energy. They had a secondary effect that people were more worried about during the Second World War, and that was the true motivation for getting this technology to show up. Now, once people figured out that you have these very, very intense source of neutrinos, then you can start thinking about building an experiment. And as I wrote down before, I'm going to write these reactions because they're useful. People figured out, and I'll use this some modern notation, the physics reaction that you can use to detect a neutrino. I always get this wrong. Is this one. Again, this is a variation on beta decay. Remember, beta decay is a neutron going to a proton, an electron, and a neutrino. I can run the movie backwards and I can put the electron on the other side. It becomes a positron. So this is the experiment you'd like to do if you have a very intense neutrino source. Protons are easy to come by. So anything has a bunch of protons. One thing which is pretty popular for target is a radioactive, hydrocarbons, complex organic molecules have a lot of hydrogen that you have access to. If you never ever think about experiments, people have done experiments with hydrogen. That's a thing you can do. Nowadays, nobody talks about that because hydrogen is very dangerous. So you don't want to have a lot of hydrogen underground, under pressure, and bad things can happen. But hydrocarbons are good because they have a lot of carbon that you don't care about, but they have a lot of hydrogen hanging around, if you remember organic chemistry. So this is the reaction that you want. You need an intense neutrino source. You need a lot of protons. And then, of course, you have a signal that consists of electrons and neutrons. And now this is where the experimental part becomes very important. And you hear about this a lot next week from the neutrino lectures. Even though the flux is very large, you need a huge detector. So your detector is not a very refined small object. These are very big detectors, even in the 1950s. And if you have a really big detector, there are many more things that the detector will start detecting, whether you like it or not. So cosmic rays are a huge problem, for example. So the question is, how do you identify these very, very rare events relative to everything else that's going on in your detector? And the really big deal with this particular reaction is the neutron, it turns out, because people figured out that if you build a detector that can see the positron and the neutron, then that's a great way of telling a background event from a real event, because it's very rare that you produce a positron and a neutron at the same time. Actually, it's much better than that. It turns out you get a positron, and then the neutron sticks around for a little bit in your detector before it gets detected. So you know that if you see a positron, and then after, I don't know, 2 microseconds, you see a neutron, that's a good neutrino candidate event. So that's how the experiment was done. And this is very, so I have some details up there. Positrons, they always hit some electron somewhere and they give you a gamma ray. The neutron, what happens is the neutron gets absorbed by some nucleus that likes to do that. That nucleus goes into some excited state, and then it de-excites by emitting a lot of gamma rays. And then the gamma rays are your signal. So it makes for something that the experiments can see very well. There's one thing which is kind of neat, which some people have heard about and other people have not. Again, the key issue is that you have an intense neutrino source. It turns out, this is the Rynason Cohen experiment. They had a proposal before the successful experiment, which is a really interesting proposal. And again, this is in the context of the Second World War. This is their original proposal to detect neutrinos, it turns out. Because there's another intense source of neutrinos, which is, let's call it a really, really fast nuclear reactor, which is a bomb. So if you have a nuclear bomb, everything that happens in the reactor happens in the bomb much faster. And what happens is in the US, they had this test facility for nuclear bombs. So they would blow them up to see how they work and measure stuff and so on. So they have this really cool proposal, which, by the way, was not funded, but it was still a nice proposal. So this is where the bomb would explode. So apparently that's how bomb explosions will look like. So all you have to do is to put your detector right next to the explosion, and then the flux of instantaneous flux of neutrinos was really large. Now, so this is a fun, so there's this 137 feet here. That's just to be funny. Apparently people were funny in the 1950s too. And now the big challenge with this experiment is that along with this very large flux of neutrinos, a bomb just went off right next to your experiment. That's very bad for your experiment. You don't want a bomb to explode next to your experiment. For many reasons. If you only care about the experiment, the worst reason is the experiment shakes, which is clearly not good for your experiment. So they had a great solution, which was, so they build this a deep hole, and then they would have the detector suspended from the ceiling. And then when the bomb went off, they would release the detector. So the detector would be in free fall, which is great because then it doesn't care that the ground is shaking. And then if you read this very carefully here, it says feathers and foam rubber. That's for your detector to fall into the, yeah. I think they could have figured that out. But yes, nobody would be there to cut the wire. But they have a line, so I think that would have been easy, yeah. So this was the proposal, which didn't work out. It turns out the instantaneous flux from the nuclear reactor is a lot less than the bomb exploding, but the integrated flux is much larger, because you can wait a long time to accumulate your data. So anyway, that's just a little bit of history. So this is then the discovery of the neutrino. And this is very important to know, this reaction and the details of the experiment, because a large subset of neutrino experiments still work this way. So reactor neutrino experiments still use the same reactor to measure neutrinos coming out of a nuclear reactor. And nuclear reactors are still a very powerful source of neutrinos that you can use to do experiments with. And I'll talk a lot more about those later on. There's another exciting thing that happened in 1958, which is we managed to figure out what the helicity of the neutrino is. And this is something that's important for different things. I think this is bothering me. Okay, that's worse, but different, so that's better. Okay. Okay, so what was also going on in the 50s is that the details of the standard model of weak interactions were being determined. And like I said, Fermi wrote the Fermi Theory. There's one thing which is still to be decided, which is what's the nature of the current. So like I said, the electromagnetic current is a vector current. And I said that the language you can use to describe these weak interactions is also using this current language. And again, this is a little bit more detailed than we need to know, but you can have what's called a scalar current or a tensor current or a vector current. And then you can have what are called chiral currents. You can have what's called a left chiral current or a right chiral current. And one big debate that was going on for the weak interactions is what was the nature of those currents that describe the interaction. When Fermi wrote the theory down, he didn't care very much because the difference is not very significant in terms of rates that you get for processes and so on. What changes a lot is, for example, the angular structure of your theory and some observables that were harder to measure. The reason I'm mentioning this is to talk about the neutrino helicity, but also to tell you about remind you of another story that's very important, which is this: what's the nature of the weak interactions? Even if you've never taken a quantum field theory class, if you're curious about the history of particle physics, one thing that people often would talk about was the fact that the weak interactions are what are called a V minus A interaction. V minus A stands for vector minus axial vector, which also means it's a purely left-handed theory. And this is something that when you're learning about the standard model, it's one of the key determining features of the weak interaction. Okay, so if that did not make any sense for you, it doesn't matter. What makes sense is that this took a really long time to figure out. So between the Fermi theory, which is in the 1930s, and the final determination that it was a V minus A interaction, all logical possibilities were considered at one point or another in the intervening 30 years of physics. And all of these things, so at some point everybody thought it was I can't remember, tensor minus scalar interaction. That was very popular for a while. And this is one case where the problem was that we learn all of these things by studying beta decay. So that was the main source of weak interactions. And the problem is that beta decay is really hard because it involves a lot of nuclear physics at the same time. And some of the measurements were very difficult. So this is one time in physics for about 20 years or so where the experimental results changed with time. A bunch of experimental results would point in one direction, and then the next round of experiments would point in a totally different direction. And eventually, this confusion was resolved by theory. So some theorists said, it has to be a V minus A interaction. These other ideas are just crazy and wrong. It's not a very strong argument, but they turn out to be correct. And then there are two groups of theorists associated with that discussion. But all of this is to say that one thing that was an interesting measurement is when the neutrino gets produced, is it produced in a polarized way? And this is something that, again, is very important at that time because of the idea of parity violation. So people figured out that parity is maximally violated in the weak interactions. So that's why I'm talking about this. And the experiment that's done is a very complicated experiment, and I'm not going to go into the details. Because remember, whatever you're doing in these experiments, you're not measuring the neutrino. The neutrino does nothing. It just goes away. But it leaves an imprint in the rest of your experiment. So what was studied was electron capture on europium-152. So this is the physics process that you can study. In this electron capture process, it's a weak process. So that means that, again, it's another version of this, where this time the electron is on this side and the neutrino is on that side. So the electron gets absorbed. It changes the nucleus into samarium-152. And it turns out that a neutrino goes out. And this samarium here has spin 1. And it's an excited state. And then the samarium will decay very quickly into a photon. And this is the physics process that happens at the end. So eventually what you have is electron, europium going into photon, neutrino, samarium. And what happens is, by looking at the direction in which the photon would go, and by assuming that angular momentum is conserved, then you can determine what the spin of the neutrino is doing in this interaction. Now, I don't want to talk more about this. I thought about giving this as a homework problem to understand what's going on here. Yeah. We'll talk about that later. But for now, I'm just talking about the observationally correct statement, which is in any experiment we've ever done, we can establish that all of the neutrinos come out as left-handed with the level of precision that we can do the experiment. As you said correctly, if the neutrino has a mass, this statement cannot be absolute. It has to be violated. But it turns out to be violated very, very little. But we'll talk about that more. I'm just saying that this was a really big event that people could determine experimentally that all of the neutrinos that are produced via weak interactions are left-handed. All of the neutrinos produced in a nuclear reactor are right-handed because they're antineutrinos. And anyway, so this is one of these important dates. I don't want to talk about that very much. The next point, which is very important, is another big debate, which is this one is a great story, and I'll talk about that a little bit, which is, remember we discovered pions, or we talked about pions, and it turns out that the pion likes to decay this way. And then I also talked about neutrons, so let me write that again. This turns out to be an antineutrino. And we were very sure about that. We also knew about the muon. So the muon likes to decay this way. So that's how people would describe all of these processes in the 1940s, let's say, when after the pion was discovered, and we figured out that that's what was going on, and we figured this decay out as well. This decay, by the way, is very, very similar to this one, except that you have an electron neutrino current, this one, combined with a muon neutrino current as well. So these were the processes that came up. And then a very, very obvious question you can ask is, are all of these neutrinos just one neutrino? And of course, that's what everybody believed, because that's the most reasonable thing you would assume, right? I'm sure you've all heard of this because you've all taken particle physics. You know for a fact that these neutrinos have labels as well, and they're not the same particle, right? So the question is, when did we figure this out? And experimentally, this was figured out in 1962. And I'll talk about that in just a second. This is a Nobel Prize winning experiment, which is also how we do all neutrino experiments today. So that's why I'll spend a little bit of time talking about that. But the reason that we started doubting whether there was only one neutrino comes from a combination of theory and experiment, and it's related to the muon. So you probably know about this, or maybe if you don't, I'll talk about the muon. The muon is a very interesting particle. So again, the muon was discovered but not identified in the 1930s. And eventually by 1947, we were very sure that there is this thing called a muon. We started studying the properties of the muon. And as far as we can tell, the muon is just like an electron, but it's heavy. Right? So you've all heard this before. So that's how you want to think about the muon. And once that was identified experimentally, there's a very, very famous quote about the muon, which is, who ordered that? So you've all heard this before. So, people were saying, okay, so the quark, the up and the down quark make up the matter that we observe, blah, blah, blah. And the neutrinos show up in, beta decay. But the muon was this, new copy of the electron, which was heavier. And it wasn't good for anything. So that's the context for the muon. The muon, in modern language, it was the first second-generation particle that we discovered. So the idea is, how do I make sense out of a muon? Because it has all the properties of the electron except that it's heavier. And one very good way of making sense out of the muon is to look at nuclear physics. So we know, for example, that you can have, say, a chlorine nucleus, but you can also excite the nucleus and make an excited chlorine nucleus. It's the same nucleus, but it's an excited state. So, it has, if you could measure the mass of that, the mass would be a little bit different. So one hypothesis that people raised immediately was, well, maybe the muon is like an excited electron, right? Which makes sense. They have the same properties, so maybe that's what the muon is. And that would be exciting because it would give you some internal structure picture to the electron, for example. That was the first thing people thought about. And then, of course, if it's an excited electron, it should decay by emitting gamma radiation. So the question is, maybe the muon knows how to do this. Which, of course, is a totally reasonable question to ask. This is a nice physics process. It's a two-body decay. It conserves charge. It conserves energy and momentum. It conserves angular momentum. So why not? So people started looking for mu to E gamma immediately. So after they identified this is how the muon likes to decay, they said, well, does the muon decay into an electron and a photon? So this started off in the late 1940s or so. And this is measured in terms of branching ratios. So, so they figured out the branching ratio can't be 10%. It's not 1%. It's not 10 to the minus 3, 10 to the minus 4, 10 to the minus 5. Nowadays, the bound is about 10 to the minus 13. We've never seen this happen ever. Okay? Now, this is a big mystery because we knew that the muon can decay this way. Okay? And this is a big problem because, or not a problem, but you can make a prediction. If the muon knows how to decay this way, then it has to decay this way as well. It doesn't have a choice. And the reason is, if you want to think about it without using a quantum field theory language, is that if the muon can decay in this way, because this is a neutrino and an antineutrino, it's a particle-antiparticle pair, they can annihilate into nothing. Okay? So I can have the muon going into an electron, nu bar. The nu bar can annihilate into nothing, except that this doesn't conserve energy and momentum. But of course, both the electron and the muon have charge, so they participate in the electromagnetic interactions. So they could radiate off, so the idea is to say this electron here is a very, very virtual electron, but it can radiate off a photon, and then it would not be virtual anymore. It would be a real electron. So you can have a photon over here. So the fact that this happens implies that this must happen. Okay? It's a fact. You can't not do that. And better than that, you can estimate what the branching ratio for this has to be. And it's something like 10 to the minus 4. Okay, just by doing the calculation. It's an easy estimate to make. And even if you do it wrong, you get the answer that's like 10 to the minus 4. Okay? So this is your prediction for the rate for mu to E gamma, even if the muon is not an excited electron. Because this decay happens, this has to happen. And of course, it didn't happen. So what's wrong with this picture? And people puzzled over this for a very long time. until somebody says, hey, maybe these two neutrinos are not allowed to annihilate into nothing. Maybe they carry a quantum number that makes one different from the other. So that's the idea. So what you do is, in order to say that this doesn't happen, you invent a new quantum number, or you invent two new quantum numbers. You invent something called electron number, which is conserved, and muon number, which is conserved. So the muon has muon number 1. The electron has electron number 1. So this decay violates both electron number and muon number. That's how you solve this problem. And then a side effect of doing that is that now you've invented a new neutrino. Because the pion has no muon number, the mu plus has a muon number -1. So this neutrino here has muon number +1. Otherwise, this decay wouldn't happen. So we label it with a mu like that. The neutron has no muon number or electron number. The proton has no electron number or muon number. The electron has electron number 1. So this antineutrino has electron number -1. And then this reaction can happen. And then this decay here, this has muon number 1. So this has muon number 1. This has electron number 1. So this has electron number -1 to conserve muon number. So the end of the story is that you've just invented a second neutrino because they carry these different quantum numbers. So there are different particles now, the electron neutrino and the muon neutrino. And the reason this was invented was to make sure that this didn't happen. So mu dui gamma forced you to invent a second neutrino. This was called the two neutrino hypothesis because now I have two. And the question is, how do I verify if this hypothesis is correct or not? And that's the 1962 Brookhaven experiment led by Lederman, Steinberger, and Schwartz. Again, these three people got the Nobel Prize for this experiment. And it's a very clever experiment. So I will explain in pictures. So the idea is very simple. You want to study neutrinos in the laboratory. The challenge is always the same. There are no neutrinos around, so you have to make them. So to make neutrinos, you either want a nuclear reactor or you need a particle accelerator. And we were starting to build bigger and bigger ones starting in the 1960s. So the idea is you take a lot of protons, you make a beam out of them, you shoot them on a target. So again, you will hear a lot more about this in the next week. So you shoot protons on some target. And when you do that, if the energy is high enough, what happens most of the time is that you produce a lot of pions. Okay? So hopefully, if I say something that you don't know, just stop me. But I'll assume that you're familiar with basic things like that. So you produce a lot of pions of all types. The pi zeros, we don't care. They decay into photons ridiculously fast, and then nothing happens after that. The pions, the charged pions are the ones we care about. Like I said, these charged pions decay, and they decay into a muon and a neutrino. So what happens then is, if you shoot protons on a target, you produce a bunch of pions which decay. This is just like what happens in the atmosphere. And then the pions decay in the right way into a muon and a neutrino. Okay? So now that means if you can get these pions to go in the same direction, they will decay eventually. They will all decay and give you a lot of muons and a lot of neutrinos. Then what you do is, so the system here is moving forward. So this has some momentum, so all the particles kind of go forward. If you want to study these neutrinos, you put a lot of material in the middle, like here. And of course, as the muons and the neutrinos go through the material, the muons get absorbed, the neutrinos don't care, so they just go through, and then you put your detector here. So basically, in this complicated way, you get a lot of neutrinos coming out on this end, and then the neutrinos get to your detector. And of course, you need a very large flux because the probability that the neutrino will hit something is very small. Okay, so you've built that, and the question that they were asking was the following. So my neutrino now is going to hit my detector, and when the neutrino hits the detector, it'll do something similar to this. And the way that we like to talk about that is that the neutrino hits something and produces a charged lepton. Okay? If the energies are high enough, just like you can produce a positron in this reaction, you can produce an electron if the charges are correct, or you can also produce a muon. So you have these two possibilities. So you have a neutrino, it can hit something and produce a muon, and hit something and produce an electron. Okay, so these are all the logical possibilities. So if the two neutrino hypothesis is wrong, that means that when this neutrino hits something, it doesn't care whether it produces a muon or an electron. It can produce either one. And you expect that producing an electron is easier because the electron is so much lighter than the muon. So just from phase space, producing the electron should be easier. However, if this two neutrino hypothesis is correct, these are muon neutrinos. And if this is a muon neutrino, when it hits something, it has to conserve this muon number. So that means that the muon neutrinos can only produce muons, and they can't produce electrons. It would not be possible. So this is the experiment that was done. So you produce a muon neutrino beam, and you see if the muon neutrino beam only produces muons in the final state, or whether it can produce electrons as well. And they did the experiment, and it turns out that it only produces muons. It never produces electrons. So this is the experiment that's called the discovery of the muon neutrino sometimes. And like I said, it's a Nobel Prize winning experiment. So is this one, by the way. The experiment that discovered the neutrino is a Nobel Prize winning experiment. There's an unusual fact that this experiment got the Nobel Prize before that one. By a lot. But anyway, we don't count. So that's an interesting thing that happened. And the reason this is such an important experiment is that this is how we still produce neutrino beams today. It's exactly the same thing. We just know how to do it bigger. But the physics is exactly the same. So we don't know how to do better. One thing we would like to do better is to exploit muons and then get the neutrinos from muon decay. The problem is that's really hard because the muons are what's called a tertiary beam. So the initial beam, the primary beam are the protons. The secondary beam are the pions. So the muons are a tertiary beam. So if you got the neutrinos out of muon decay, you're really suffering dramatic losses in terms of flux because you only control the protons. That's the thing that you can put in your machine. Everything else is at the mercy of the particles decaying, the fact that you can't collect the particles and steer them around efficiently. So people are thinking about how to do that, but we still don't know how to do that, and it's very expensive. Okay, so the last thing I want to talk about in this history is the fact that, so number 3 there says 1962. The next exciting event for neutrinos is only in the 2000s. So if you neglect neutrino oscillations, a bunch of other stuff happened, which I'll just say very quickly. The most relevant one for us is that we discovered the 3rd generation. Yeah. That's a very good question. So the question is, why doesn't the pion do this? The answer is it does. It's a quantitative question. So what happens is this decay happens 99% of the time. This decay happens 10 to the minus 4%, 10 to the minus 4 of the time. So it's a very, very rare decay. Also, it took people a long time to measure this. There's another work of Steinberger that measured the rare pion decay. This is called Pi-E2. And this is a textbook particle physics question, which is why is this decay so rare? So do people know? Because of? Yeah, it's the helicity suppression. So do people know this? So let me just say one very important hint. If you want to be a particle physicist, you have to know this. It's required. Before you get a job, people will ask you if you know this. If you say you don't know, they don't give you a job. So this is really important. And again, it's because of what's called helicity suppression. So what happens is I don't know if I can, I'll probably say things that some people might not know, but this is a weak decay. And it happens by this V minus A interaction. So what happens is when the decay happens, the interaction has a particular requirement for what the spins of the particles are supposed to be. Okay, and I'm saying this in some, so the idea is the following. Here's your pion. It decayed in this way. So the neutrino went this way, and the positron went this way. Okay, this is a weak interaction process. So in the limit where you don't care about particle masses, the helicities of the final states are completely well defined. So what happens is this is a neutrino. Remember I said all neutrinos ever produced in the universe are left-handed? This one is left-handed. So let me indicate that by drawing an arrow. So I'm saying the spin and the momentum are going in opposite directions. Okay? Now this is a positron, which is also being produced in a weak interaction process. And because it's being produced in a weak interaction process, the weak interactions want this positron to be right-handed. So it's the same reason as for the neutrino, except that the positron is the antiparticle, so the spin is the opposite one. So that means that's what this guy wants the positron spin to do. Okay? So if we didn't know what the pion was, this is what the decay would look like because it's a weak decay. So it wants to produce a right-handed positron and a left-handed neutrino. The problem is if you look at these spins, they're both pointing the same way. So this state here has spin 1. Okay? But the pion has spin 0. So the pion can't allow for this to be true. The pion doesn't like that. The pion has no spin. That means that one of these spins has to point in the wrong direction. It can't be the neutrino, it has to be the positron. So the positron comes out with the wrong helicity. And this is the part that you have to believe me. The positron is allowed to do that because it has mass. That means that the amplitude for this process is proportional to the electron mass. Okay? So the lifetime of the pion is proportional to the electron mass squared. And everything that I just said for the electron final state is also true for the muon final state. So that means that the partial width for a muon, the final state, is proportional to the muon mass squared. And the muon mass is way bigger than the electron mass. The electron mass is half an MeV. The muon mass is 100 MeV. So it's a factor of 200 squared. That's a really big number. That's the 10 to the minus 4. This is not totally true because there's some phase space piece to this. But that's why this decay is way, way more common than that one. And I'm not doing the calculation justice because you have to do the calculation yourself. But that's the physics that happens there. So that's why when we talk about these neutrino beams, we don't really care about the electron neutrino contamination to the beam. The real contamination that we do care about is from the muons. Because the muons will decay in this way, and then you get some electron antineutrinos from the muon decay. Those are the ones you care about more. And you can control for that basically by saying that if the pions don't have a lot of room to decay, then the muons will mostly die inside of this beam dump, and then they will decay at rest. And that will give you neutrinos with a different energy than the neutrinos that are coming from the pion decay. So it's a very different population in terms of energy. But that's the biggest contamination. So if you know about, say, the oscillation experiments like NOVA, T2K, DUNE, the contamination they worry about the most is the one from muon decay. The other thing they care about, just to be complete, is it turns out that when the protons hit the target, you don't only get pions. You get other things like kaons. If the energy is very high, you get charm mesons and so on. Kaons are different because they can produce more electron neutrinos than the pions because they can undergo this decay here. Wrong, correct. They can undergo this kind of decay, for example. And this is not, so the language people use is that this Brunchy ratio is very small because it's helicity suppressed. This is not helicity suppressed. That means that here everybody can have the right helicity final state. Okay? So yeah, we can talk a lot more about this if people are interested. But the idea then is that in the 70s, the third generation was discovered. The tau particle was discovered in 1976 or 4, I can't remember now. It was also a Nobel Prize winning experiment. And so together with the tau, people discovered the bottom and eventually the top quark. And of course, if you discover a third generation, the question is there a third generation of neutrinos? And the tau is very much like everybody else. So if you have a tau, it can undergo weak decays into, for example, I don't know, this is one logical possibility. The tau is very heavy, so the mass is 1,777 MeV. So it has a bunch of final states it can decay into. This is a very rare one. It likes to do other stuff like this. So taus are very messy, but there's another neutrino here. This is wrong. So that's the physics. So once you postulate that this particle here exists, and it's not the same as this one, nor is it the same as that one, you'd like to verify that experimentally. So you want to be able to produce a tau neutrino and have the tau neutrino hit something. So how do you do that? It's the same idea. So you shoot protons on a target. You produce other mesons which are not pions. In particular, there's a meson that decays into a tau and a neutrino called the d sub s. That's a charm strange bound state. For the same reason that the pion likes to go into muons, the d sub s has an affinity for decaying into taus. The problem there is that the tau is super heavy, so you get a phase space suppression that makes it a little bit smaller. But nonetheless, if you produce charm mesons, they can decay into taus and tau neutrinos. If you do your dump, then you get tau neutrinos in the final state, and then you detect them in the detector. And the question that you ask then there is, if I have a tau neutrino, does it know how to produce a tau in the final state? So it's the equivalent of this question. So I have a tau neutrino. It hits something, produces a tau, and then it produces something else. Okay. So the question is, how do we observe this reaction here? And it turns out that this is a very, very difficult experiment because, so like I said, if you hit the target with a lot of energy, you can produce, say, one of these d sub s mesons. This decays into tau and nu tau. You put this in a dump that eats up all the taus. You're left with the new taus here. So it's exactly the same experiment. So why is this experiment so hard? This experiment is really hard because in the process of producing this tau neutrino beam, you produce all the other neutrinos that you don't care for in this particular experiment. And you can't not do that because pions are very easy to produce. So even though you say that you have a tau neutrino beam, the fraction of tau neutrinos in that beam is like 1%. So on top of all your tau neutrinos, you have everybody else. So you have to keep that in mind. And those are impossible to get rid of. Then the question is, how do you see the tau? And the real issue is you have to see the tau in a way that's distinguishable from everybody else. And the best strategy that people had, and that's how they discovered the tau neutrino, is to take advantage of the fact that the tau has a finite lifetime and that the tau can decay into a muon. So again, not to get into the details of the experiment, the idea is the neutrino comes in, hits something, produces a tau. The tau moves about some fraction of, a couple of millimeters in your detector, and then it decays into another final state, which is this one. And you see this muon here. Okay? So this muon comes out, and this decay kind of goes this way. So the muon goes here, one of the neutrinos goes here, the other one goes there. You don't see the neutrinos, but you see the muon. And the key thing is, what you can see in your detector is that nothing comes in, it gets hit, you produce a charge track, and then the tau decays and produces another charged track. Muons are very nice because they don't interact very much, so they can travel a very long distance in your detector, so they're very easy to identify. Okay? So this is called a kink signature because you have a track that all of a sudden changes direction in a very abrupt way, and that's a sign that those two neutrinos here were emitted. Okay? This is the tau discovery experiment, and the way that they looked for that is to look for kinks. Technically speaking, this requires exquisite vertexing, so you can see this very, very tiny track, and you need a very special detector for that. Your detector also has to be very dense because we're talking about neutrinos, so the cross-section is very small. So that's the challenge. This particle was discovered in 2001. If you discount the Higgs boson, this was the last standard model particle to be discovered. The top quark was discovered in 1998 or 7 or 5, something like that. Okay, 6, yeah. So this was 5 years after the top quark was discovered. And there's another fun fact, which is if you look at, say, the Higgs boson today, we have a very healthy bump of Higgs bosons in the LHC. So if you like to count how many Higgs bosons we've identified, that number is of order 100 or so. The number of tau neutrinos that's ever been observed directly is like 8. Okay, literally. A little bit more, it's like a dozen. But that's all the events that have been individually identified as a tau neutrino. So that's the world sample of that. And I like to show, so the experiment that did this is called the donut experiment. And it's a marvel of data analysis, if you like data analysis. So this is how these kinks look like in the donut experiment. This is, I think there are 2 events here because there are different angles looking at the same event. And these are these kinks that I was talking about. So a tau is here, it produces a muon. Another tau is here, produces a muon here. The real detections are these points. So you have to be imaginative sometimes to see where the kink is. But it works quite well. So these are the events that were identified in this experiment. It looks very easy. You know, you can see these tracks by eye. Now, this is a passive detector. That means that this is a detector where all of the tracks are recorded first, and then so you don't see one track at a time. You basically send all of the neutrinos in. They make all the tracks that they want, and then you analyze all these tracks at the same time. And the real experimental data look like this. So this is your data. So you have to find one of those tracks there. And they did, you know, they found like 6. Not in this, so every data set looks like that. So they have this magic algorithm that cleans out their data set so that you end up with something that you like. So it's a really, really hard experiment. And a lot of the technology, by the way, that's associated to this is, so this experiment does look like a photograph, these detectors. You know, so you have this very big plate, which depends on the size. Let's say it's this big for this, you know, order a fraction of a meter square. And the charged particles leave a little dot there. So you have to go and find all the dots in this square. So this used to be done by hand. These experiments were very popular in the 60s and the 70s. So if you were a grad student back then, your job was to have a microscope and just very, very slowly go through this meter square, counting all the little dots. The really big deal here is that this would take, you know, 100,000 years to do the experiment. So they were very good at making the computer do this. And that turned out to be very, very challenging. And it's a big effort by a very strong component of the Japanese group in this donut experiment that knows how to do that. And that's why people still talk about maybe doing experiments in this way, which is very hard. There's something called the opera experiment that also used this emotion techniques in a very interesting way that I don't want to talk about. All right, this is where we are. So we've discovered that there are 3 neutrinos and they interact via the weak interactions. And the last piece of the puzzle was laid in about 2001. And here's a nice summary of how everything was going really well until something bad happened. But this is the idea, and I think this is important because this is sort of a, if you've taken a particle physics class, and from somebody who doesn't care about neutrinos, this is probably what they had to say about neutrinos. So there are three flavors, you know, the electron, the muon, and the tau are called the neutrino flavors. Some people also refer to them as weak eigenstates. And the flavors are associated with what's the charge lepton that comes out when this neutrino is either produced or detected. So the electron neutrino is friends with the electron, the muon neutrino is friends with the muon, the tau neutrino is friends with the tau. And that's what was used for all of these discussions that I've just led. So there are three of those. They only have weak interactions. One issue that we'll come back to very, very recently is the fact of the neutrino mass. And I will come back to this probably in a couple of lectures. But one of the predictions of the simplest version of the standard model is that the neutrino mass is 0. And I'll talk a lot more about this later. But the standard notion was that the neutrino mass was 0, or if you're a very pragmatic person, you would just say that it's really small. Okay. And most of what we'll talk about for the next 3 lectures is what do we know about neutrino masses. And like I said, you know, there's a left-handed neutrino state and a right-handed antineutrino state. These states are related by CPT theorem. I'll talk a lot more about this probably in the next lecture because this is also important. So this is the picture that I want to leave you with before I start talking about the next thing, which is when does this picture go wrong? And experimentally, this happened in the 60s. So I will leave this timeline that I was discussing, then I'll go back to what's called the Neutrino Anomalies, or the Neutrino Puzzles. So, going back to this picture, the main message is the following. If you produce an electron neutrino and it hits something, it produces an electron. If you produce a muon neutrino and it hits something, you produce a muon. And if you produce a tau neutrino and it hits something, it produces a tau. Okay, that's the rule. And that's associated with this conservation law, which I said was invented to explain why mu to E gamma doesn't happen. So in a nutshell, what we've observed in the last 50 years is that this is actually wrong. So it is possible to produce a muon neutrino and detect it as a tau neutrino. That means a muon neutrino can hit something and produce a tau, or something that was produced as an electron neutrino can hit something and behave like a muon neutrino or a tau neutrino. And the evidence for this is absolutely overwhelming. Okay, so again, if you don't want to remember anything else, this is also something that, that was not true 20 years ago, but nowadays we are very, very sure that this phenomenon happens. The other hint, which I'll talk about in detail, is that this phenomenon depends on the distance, and it depends on the neutrino energy. Or if you combine those two pieces of information, it actually depends on the neutrino internal clock. So it depends on how much time has elapsed in the neutrino's rest frame. And it turns out that these phenomena depend on you waiting a very long time in the neutrino's rest frame. So it's a time-dependent phenomenon. Okay, that's what we're very, very sure of. So what I want to do for the rest of today and probably for most of tomorrow is to talk about what these data are and how we resolve these puzzles and why that has something to do with neutrino mass. All right. So let me start with the sun. Okay, so we will have to learn a little bit of astrophysics, and Fabio will teach you a lot more. So I will just give you the particle physics version of astrophysics, which is this, by the way, is another of these fundamental problems in physics, which is how does the sun work? This is something that I think Newton talked about, or people after Newton talked about, probably after Newton, but not much after. And they were very confused about the energetics of the sun, because the energetic output of the sun is wrong. It's not clear how the sun does that. If you just count, say, the gravitational energy of the sun, or the chemical energy of the sun, it's outputting way more energy than it's supposed to. The answer to that is nuclear physics, is that you have access to the, if you want, the nuclear energy of the sun. So the energy that's stored in the masses can be slowly converted into energy in electromagnetic waves. And that's how the sun can effectively produce all this energy. So before the E equals mc squared, we didn't know how the sun worked. Even then, it took a very long time to figure out how the sun works. We made a lot of progress. And to make a really long story short, the sun works by nuclear fusion. Okay, so nuclear fusion is effectively, you take a bunch of protons, which is mostly what the sun is made of, you convert them into helium, and helium is this very, very tightly bound nucleus. So you gain a lot of binding energy when you do that. So that binding energy is emitted in the form of electromagnetic radiation and neutrinos. How do we know that? Because to convert 4 protons into a helium nucleus, you need the weak interactions. Because you have to turn 2 of those protons into neutrons. And in the process of doing that, you emit positrons and neutrinos, electron neutrinos to be exact. So these are all of the nuclear reactions that participate in making the sun shine. And they're effectively converting protons into helium-4, like at this step over here. You can burn the helium-4 too, but it's not as efficient. And if you know about how stars work, at some point our sun will be a helium-burning star, but that's when it's kind of going downhill. It's kind of dying, and we won't be around for that, I suspect. Well, I hope we're around for that, but that's a long story. We, but meaning everybody we. Anyway, so this is how the sun works, and the key point is neutrinos are produced everywhere. So it's a generic prediction of something called the solar model, that you should see neutrinos coming from the sun. And what's nice is you can calculate not just how many neutrinos you expect, but what their energies are supposed to be. Because these are all nuclear physics reactions, which in principle you can measure in the laboratory. And the same thing that happens in your laboratory is happening in the center of the sun. There's a fun number you want to keep in mind to talk to your astronomy friends. If you're in particle physics, the sun is a really, really cold place. Nothing interesting is happening in terms of kinetic energies of anybody. Everybody's too heavy for the sun. So the sun is really cold, so measuring something in the laboratory is just like in the center of the sun. So that's important to know. So you need like a supernova as a very hot place for particle physics. The sun is not so hot. So, like I said, we can calculate the flux of these neutrinos, and we can calculate the energy, the energy spectra and the total amounts. This is a very confusing plot, which includes a lot of lines, and every line is associated to one of these nuclear reactions that I talked about. So they give you a spectrum of neutrino energies. And then there are also these lines, and these lines are for 2-to-2 processes where the energy of the neutrino that comes out is well defined. It's a 2-body to 2-body reaction. Like I said, the amount of kinetic energy allowed is very small. I mean, initial kinetic energy is very small, so you know that the neutrino comes out with a well-defined energy. That's what these lines here represent. And all of these lines have names. Nowadays, nobody cares anymore, but it used to be very popular to know all these names. So these are called the PP neutrinos, very low energy neutrinos. These are called boron-8 neutrinos. They're very high energy neutrinos. You have the beryllium-7 neutrino line. You have this PEP line. And then you have this HEP flux. And this is the one that goes to the highest energy. But you notice that most of the neutrinos are these PP neutrinos. Just if you look at this, this is a log scale. So this flux is gigantic. This flux is very small, and this one is really small. However, when we try to measure neutrinos, the cross-section for neutrino detection scales like the neutrino energy, or sometimes the neutrino energy squared, depending on the reaction that we're talking about. So there are many, many reactions where we can actually see these neutrinos, but we can never see those, because not only is the cross-section very different, but on top of that, if you have a very low energy neutrino hitting something, the products of that reaction will also be very low energy. They're very hard to detect. So if you need your final state particle to have some energy so you can see it, it pays off to see the high energy neutrinos. And finally, this plot here has these colors. And these colors represent different types of neutrino detectors that people built in the 60s and the 90s, 60s, 80s, 90s, and 2000s to detect neutrinos. And these colors indicate the threshold for these types of experiments. We have something called the Super K experiment and SNO. Their threshold is at a several MeV. They've managed to move this down to maybe 4-ish or something. You have something called the Chlorine Experiment. Then you have the Gallium Experiment, and they have different thresholds. So I want to talk about these experiments for a few minutes, and then I'll talk about what these means. These are very important historically experiments, and they measure the neutrinos in very different ways. So I want to talk about that. If you're thinking about how to measure a low energy neutrino coming from the sun, so again, these are neutrinos with energies, which I should have pointed out. These are in the MeV or 100 keV range. It's a nuclear physics process. These are nuclear physics energies, so that's not a surprise. The first idea people had was to use beta decay. And actually what you want to do is you want to use inverse beta decay, which is the following. So remember, the neutron decays in this way. If I take this neutrino and move to this side of the reaction, I can get this process here. And then if I dress this up into some big nucleus, then the neutrino can come in and turn one big nucleus into a different big nucleus emitting an electron. And one kind of experiment you can do, which is very hard, but that's what people did, is you can look for this nucleus here. So the first experiment of this type is called the Chlorine Experiment. And the idea is very simple. You take a lot of chlorine, you put it deep underground where nothing else is going to get to it, and then you wait. And then the neutrinos go through your tank, and what happens is chlorine gets turned into argon. I think it's 37, but I'll probably get it wrong. So you have a really big tank of chlorine. As the neutrinos coming from the sun hit the chlorine, they convert the chlorine into argon. So why is that nice? Argon is a noble gas. So it doesn't do anything in this big chlorine tank that you have sitting there. So it's not going to react, right? So that's good. So then you filter your chlorine all the time, and you do it in a way where you can extract out or bubble out this argon. That's the idea. And then as an added bonus, this argon is actually radioactive, so it decays. So that means that you can filter out this argon out of the chlorine, it bubbles out, and it's radioactive, so it decays, so you can see that you have a radioactive argon mixed into your chlorine, and this way you can detect the neutrinos from the sun. So that's the idea. So this experiment started in the 1960s. It was an experiment that was a very unusual experiment for particle physics people, because most of the challenges have to do with chemistry. They have nothing to do with particle physics. It's how do you efficiently extract argon out of chlorine in a way that you have control over what's going on. So the experiment was proposed by a Brookhaven person, Ray Davis. He found a mine in South Dakota in the United States. He convinced them to build a cavern for him, and he put a really big tank of of chlorine. Chlorine, by the way, is the stuff that you buy when you want to clean things. You've all done that. You have in your chlorine, you use that to scrub the floor and stuff like that. So it's mostly cleaning fluid. So that's exactly what he had, just a lot of cleaning fluid, a very big tank, which is not as big as this room, but it's probably about as big as a tenth of this room. Then he added deep underground in an active mine. It was a gold mine in South Dakota. Is that a gold mine? I can't remember. Good note. I think so. That's embarrassing. I'll remember that later. So it's a mine in South Dakota, and then you measure the argon. There's one number that you should be impressed by. The units in which you measure the argon is in atoms, and they would get like a few atoms per month. So that's the experiment. And this is this first bar on the left-hand side. The thing you want to look at first is the blue bar. That's the measurement of the neutrino flux from the sun. And it's measured in funny units. So it's a 2.56. This is called a SNU, S-N-U. And it's called a solar neutrino unit. And it's a very, very tailor-made unit for these types of experiments. So this is the important result. That's the result that came out in the late 60s. And the reason this result was very famous was for many reasons. One is that this is a really amazing experiment. They saw neutrinos coming from the sun, which is a confirmation that this nuclear fusion idea is correct. Nobody knew that before. It was plausible. But this was a non-trivial prediction that you make out of this picture. And the other thing that they were very famous for is that you can calculate how many neutrinos come from the sun. And that's the bar on the left-hand side, the one with the colors. And you notice that they were off by a factor of 3. So what do we do with that? And when that result came out, people just thought, hey, this is an amazing result, and we're within a factor of 3. That's also pretty amazing. End of story. However, this kept on going for about 20 years, literally. And the discrepancy persisted. The experimental result persisted. The error bars on this something called the standard solar model got better, and we understood it much better. And the discrepancy was still there and very strong. So how do we resolve that? The solution, if you asked around, especially in the particle physics community, was that there's no way that this experiment can measure this with this very tiny error bar. This experiment is just too hard. And it's run by a bunch of chemists. So we don't trust chemists. So clearly they're doing something wrong. Then the other half of the room would say that, this calculation is really, really hard. Which is true. Because if you look at their colors here on this bar, the dominant component there is the yellow color. These are the neutrinos coming from boron 8. And I just want to point out why this is so hard in a sentence or so, which is the dominant production process is the dominant fusion process is this PP going to a deuterium plus positron plus a neutrino. All of these other steps, except for this one, this is a very rare 3-body initial state process. All of these other steps, so for example, this step here requires that you understand how much deuterium you formed up there. That forms helium-3. This step here requires that you understand how much helium-3 was formed in there. And then this step here requires that you understand how much helium-3 and helium-4 is formed so that you can understand how much beryllium-7 is formed. And the beryllium and the boron, which is most of your neutrinos, are coming from this beryllium-7 proton capture process. So in order to understand how much boron you have to know all of these processes in between. Even if you don't care about any of that, just think about error propagation. If you got this one off by 1% and this one off by 10%, this thing goes in a crazy way. So the errors propagate in a very dramatic way, which means you have to understand things really well if you want to claim that you understand the flux of these neutrinos at the 10% level. It's a very, very difficult calculation. So keeping this in mind, people were very skeptical of this result, both from the experimental side and from the theoretical side. Whenever that happens, and you think this is an important problem, you build a new experiment. So they did, and in particular, they built these, I'm violating time evolution here, but another class of experiment that's very important are these gallium experiments. The gallium experiment is very, very similar to the chlorine experiment, except that you're turning gallium into germanium. I hope I got this right. And, but it's the same kind of general idea. The masses are different. The volume of gallium is about this much, not a room full of chlorine gas. And people got excited about gallium because of the threshold. So the threshold here is a much lower than for the chlorine experiment. That means that they see these PP neutrinos, and this is the neutrino flux that we can calculate really well. So they do the experiment. There are 2 different experiments, one in Russia, one in Italy. The 2 experiments eventually merged in another experiment, which I think is in Italy, but maybe I'm getting the order wrong. I think that's correct. And so these are the results of this called SAGE and GALEX and GNO. Again, in blue, The predictions are here, and we're still off. And now we're dominated by these PP neutrinos, and you notice that the PP neutrinos saturate the gallium measurement. So all the other neutrinos have to not be there in order for you to explain this as a miscalculation. This is a very, very big deal. Okay, so this is a very important experiment. So the other kinds of experiments are these very, very big water tanks. Yep. No, not at all. I'll talk about that tomorrow. 1/3 is confusing. If you want to do very, very vanilla oscillations, you could get 1/3, but you require maximally maximal mixing. And then you can get exactly 1/3. And that's the same reason you would expect to get 1/2 if you only had 2 neutrinos. But the mixing has to be maximal. So the 1/3 is a big deal. If it was 80%, people would be happy. 1/3 was very interesting. And it took it took longer to explain what was going on. So it's a very good question. So the other kinds of experiments are these water experiments. And the first one of these experiments is the Kamioka Experiment. That started being built in the 1980s. And what that experiment can do, and I'll talk a lot more about this experiment tomorrow as well, is they can measure neutrino electron scattering. So you have your this very, very big tank with water. An electron neutrino comes in, it hits an electron. And it turns out that this experiment is really good at seeing electrons, as long as the energies are bigger than something. And that's where the threshold comes in. So they can only see what's called the boromate neutrinos, the high energy neutrinos, which have the smallest flux. So the way that you make up for that is that you need a lot of water. So these experiments really have sizes which are of the size of this room or much bigger. So the Kamioka experiment was probably about the size of this room, all filled with water, and all monitored for activity so that you can see these electrons. And I'll talk a lot more about this, although people might know. The question is, why would you ever build a tank of water this big? And the answer, of course, is to see solar neutrinos. But that's actually not the answer. This was a side effect of the experiment. What's that? No, they wanted to look for proton decay. So proton decay became a thing in the 1980s, when theorists started building some weird theories about grand unification and so on, and they could predict that the proton should decay. So that means if you have a lot of protons and you monitor your volume for a long time, you should see a proton decaying every once in a while. So again, how do you do that? You build a very large tank of water and you leave it deep underground where nothing is happening. Now, why do you do it with water? So do people know? It's cheap. So water's cheap, and you can purify it, and we know how to handle water, although water is a horrible chemical. But it's very, very cheap, and there's a lot of it, and you can purify it. So that's why they went with water. But then they had to start worrying about neutrinos, because you can't shield the neutrinos. And that's how they started making these measurements. So these experiments measure electron-neutrino scattering. And that's the Kamioka experiment. This is the baby version of Super Kamioka. And their results are consistent with one another. They only measure the yellow bar, but they are definitely off by about a factor of 1/2, which is not the same as 1/3, by the way. It's different. And this experiment here, this type of measurement was confirmed by a very different type of measurement, which is not here. That's kind of disappointing. But there's another measurement from the SNOW experiment that can also see the same reaction, this neutrino electron scattering. And they can see a bunch of other stuff. But by doing those measurements, they are in agreement with those experiments as well. So this is what was going on. And then what happened then was people were, that's not what happened because the timeline doesn't work. But this is kind of what happened. So you had all these discrepancies. So people said, enough about we not understanding what's going on. How do we do the right experiment to check what's going on? And that turned out to be the SNOW experiment. That's a heavy water experiment in Canada. And since I've run out of time, I'm not going to talk about that today. I'll talk about that tomorrow. But that's a really cool experiment that measured the neutrino flux. So the idea was, how do I measure the neutrino flux in the same experiment in different ways so that I can test different hypotheses? And that's what that experiment was about. But because we still have a lot of stuff to go, and we actually started on time, which is impressive, then I think I should probably talk about that tomorrow. Unless people have questions, of course. Oh, that's right. It's right now. Yeah, I forgot. Yeah. I think Fabio ran away. Is that? Oh, there he is. Okay, good. You're up.
Okay, so questions?
Thanks. Just now that we have more time, I'm wondering if we can come back to the question of why neutrinos are just left-handed if they have mass.
Okay, so I will try to talk a lot more about this in the future, but let me just give you the okay, so here's a simple answer, which is the following. The neutrinos only interact via the weak interactions. And it turns out that if so in terms of particle physics language, they only interact with the W boson and the Z boson. So if that makes sense, they only interact with the W boson and the Z boson in a left-handed way, in a left chiral way. So this means that the object that the interaction would like to produce, as far as a neutrino is concerned, is always produced by a left-handed interaction, which means that the interactions want to produce only left-handed neutrinos and right-handed antineutrinos. That's what the interactions want to do. Now, if the mass is 0, that means that all of the neutrinos are really just left-handed and all of the antineutrinos are really just right-handed. Okay? So is that part clear, or kind of clear? This is very similar to the pion decay story that I was saying. So the interactions want to produce only left-handed neutrinos and right-handed antineutrinos, and there's no interaction that knows how to do anything different. Now the question becomes, if the neutrino has a mass, then the neutrino that you produce in the lab doesn't have to do what the interaction is asking you to do. It can't produce a neutrino with the wrong helicity. Now the probability for that to happen is proportional to the neutrino mass. So that means that if the neutrino mass were much bigger, when the pion decayed, every once in a while you could get a neutrino with the wrong helicity, and you would actually be able to learn about this by measuring the electron helicity on the other side, because those helicities are the same. So by measuring the electron helicity, you can ask what is the helicity of the neutrino that came out on the other end. And that way you can test whether the neutrino mass is large. So by not observing this violation of the helicity in the neutrinos produced in the lab, you can place a bound on what the neutrino mass is supposed to be. Now, this doesn't sound like a good answer, so I have to maybe think about a different way of saying the same thing. There's another picture, there's another fun thing that you can think about in terms of helicity, which is what's special about the mass being 0?
Speed of light.
What's that? Yeah, it's the speed of light. And the key thing about the mass being 0 is that if you have a particle with 0 mass, then helicity becomes a reference frame independent statement. Okay, this is very important, but it means that if you have a certain helicity in a certain reference frame, that helicity will be the same in any reference frame that you can think of. And that's only true for massless particles. We are very familiar with this because we use this to talk about photons. When we talk about photons, we talk about the photon polarization. And the photon polarization determines the state of that photon, and that does not depend on the reference frame. So if you have a massless fermion, it's the same, so the helicity is reference frame independent. If you have a mass, that's not true, because that means you can outrun the particle and then you can make the momentum flip, and then the helicity flips as well. So it's in that sense that a massless particle, if it's a fermion, is qualitatively different from a massive particle. Okay, so that's another bit of random information. I will try to talk more about this because this turns out to be a really big deal for neutrinos. Because we know that they have mass. I'll try to convince you of that tomorrow. And if they have mass, it turns out that you can ask whether they are Majorana fermions. And the Majorana fermion question is very confusing, so I'll try to explain that, and it will depend a lot on this helicity conversation and what are the possible helicity states that the neutrino can have. So hopefully that will become a little bit more clear once we talk about that. But I can try better. If you want to rephrase the question in a way that leads to a different answer, feel free to try.
I just wondering, it's not as easy as change your reference frame so you see the neutrino as right-handed.
No, not at all. Yeah, this is just a gimmick. I mean, it's just a gimmick is a quick way of telling a story that's not useful at all. But the key point is it's a combination of the weak interactions being purely left-handed. That statement is true. It does not depend on anybody having any mass. So the weak interactions are purely left-handed, and the neutrino mass is very small. So the consequence of that is that all of the neutrinos turn out to be mostly left-handed. And the problem is we have not been able to identify whether it's completely left-handed or if it's violated by a little bit. So in the laboratory, we don't have access to that information, even though the information, if the mass is not zero, is there. It's just that the information is very hard to get to. So just to say this one last time, when I say that all neutrinos are left-handed and all antineutrinos are right-handed, that's not true, but it's true 99.99999% of the time. So for the sake of talking about experiments and doing real-world things with neutrinos, it's as close to the real truth as you can get, even if it's violated by a little bit. That's why we talk about it that way.
Thanks.
Mm-hmm.
I didn't understand why the chlorine and water experiments aren't sensitive to the PP neutrinos.
That's a very good question. So if you look at this chemical reaction here, in order for this reaction to happen, you have to conserve energy and momentum. And if you do the math, this side here is heavier than that one. So in order for this reaction to happen, then the neutrinos have to provide a minimum amount of energy. So there's a threshold. So the neutrino energy must be bigger than something, otherwise the reaction does not happen. The water experiment is different. So that one, I didn't draw what the reaction was. I just said it in words. So let me draw it here. It's this reaction here. A neutrino comes in. It's an elastic scattering reaction. Like that. And this reaction has no threshold. Regardless of what the energy is, you always get the reaction to happen. The problem is these are the electrons in the water. They're not moving around very fast. So all of the kinetic energy that this electron will get comes from the neutrino. So what happens is a combination of many things, but the most important one is the softer the neutrino is, the softer this electron is, the less energy it has. Now you can ask yourself, how do they identify these electrons in the detector? And they do that by using this Cherenkov radiation. So the electron gets hit. If the electron is moving faster than the speed of light in water, it generates Cherenkov radiation. You get a very nice looking signal. This is pretty low energies. These are not the energies this detector likes. This detector likes energies of hundreds of MeV and more. Remember, so just as a parenthesis, this detector was designed for proton decay. The proton mass is 1 GeV, really big in the units that we've been talking about. So if the proton decays, the stuff that comes out has energies of 100 MeV or hundreds of MeV. So that's what the detector is good for. Solar neutrinos have energies of 10 MeV, so it's really, really soft. But nonetheless, they can see it, but they have a lot of background. So So you want to remember that, because the next thing I'll say is, so as the energy of the neutrino gets smaller and smaller, the energy of these electrons gets smaller and smaller. So they become harder to see, just to identify in the detector period. And on top of that, you have a lot of background in the detector at these energies. So you have radioactive stuff, gamma rays, neutrons that come in and produce a weird isotope that decays. So a lot of low energy stuff is also going on. And the signatures look mostly the same. So how do you tell those apart? The way you tell those apart is the following, and this is pretty neat because it leads to a famous picture which I don't have here, but it's really important. These neutrinos are coming from the sun. The backgrounds have absolutely nothing to do with the sun. There's stuff going on in the water. And what happens is this reaction here, it turns out, gives you an electron that goes mostly forward. So if you look at the direction of this electron, it goes in the same direction that the neutrino is coming from. And if you don't believe me, you can do the calculation yourself, and that turns out to be true. So the way that they get rid of the backgrounds is by looking at the angular distribution of these electron candidates with respect to the direction of the sun. And then they make a plot that looks like this. So they make, this is cosine of theta from -1 to 1. This is direction with respect to the sun. So, you know, so the sun is there, cosine of theta equals 1 is that way, and so on. So you do that as a function of cosine of theta. You have a lot of background. The background does not correlate with the direction of the sun, but your data look like this. And these are the neutrinos coming from the sun. Now, as the energy gets smaller and smaller, this curve starts to look like this, because the background level is too high, and then at some point you lose your ability to tell background from data. And that's where this threshold comes in. Of course, these people are very clever, so they can look at the data and scrutinize it as much as possible to try to see the lowest possible energy neutrinos they can. And they've been pushing at the threshold energy for a while, especially in the snow experiment that I'll talk about tomorrow, and also talk about why that's important. But that's where that threshold comes in. The thing which is really neat is that they have, you see this axis of events in the direction of the sun. And this is really amazing because you're doing an experiment underground and you can tell what the sun is without looking outside. You just have to analyze your data. So they have this picture of the sun in neutrinos, which is a picture of the sun taken, you know, from inside a mountain. And I don't have it, but I can probably find it. It's a really neat picture. It's kind of a cheat too, unfortunately. So if you have people seen this picture? Some of you? Nobody? Are you that young that you've never seen? So it's kind of neat. So the picture is about this big, you know, in some colors. And what they don't tell you is that the sun is about this big. The real sun is about this big. So the resolution is not great. But it's still very impressive, yeah. So it's for very different reasons. So the reason they chose the Gallium experiment is because the gallium is very, very similar to this. It has an intrinsic threshold, but the threshold is much lower. So that's what drove the decision to have that's one of the reasons they chose a gallium experiment. The other one must be from the ability to extract out the germanium from the gallium. There's one funny story which I'll just say for no good reason, which is one of the experiments was in Russia. And at some point, they saw that the neutrino flux was going down as a function of time. And this was a big mystery until they found out that somebody was going in and stealing gallium from the detector. And that's why the flux was going down as a function of time. Apparently, gallium is really expensive. So anyway, that was this is true. This actually happened. Yeah, somebody went in and stole some of the material for the detector, and then the flux of neutrinos went down in a mysterious way. I will say a little bit more about them, especially in the context of atmospheric neutrinos. The atmospheric neutrinos are really their biggest discovery, and that's in a different energy regime. That's in the hundreds of MeV to even 100 GeV, and that's the one that's really their biggest concern for the proton decay searches, it turns out. Which ones? Oh, these ones. Oh, so fortunately you always know where the sun is. No. That's why it's also a cheat that. Okay, let me not say that. It could be that you could postulate that the sun is that way, although you have to do it as a function of time. So if you think let's say you don't know where the sun started in the sky, but you know how it moves, then you could probably identify where the sun is. If you didn't know where it was to begin with, and if you don't know how it moves, then it's not possible to do the experiment. But one thing which is important, by the way, of these experiments is that these are real-time experiments. That means you see one neutrino event at a time. These experiments are not. These are integrated experiments. You have to integrate for a month, and then you ask how much argon you actually produced. So they're qualitatively different kinds of experiments in lots of different ways.
Okay, just to clarify, we're now in the discussion session, so we take questions on neutrinos, but also on dark matter. It's just free to ask any questions, okay? So next question. Just wait the microphone,
yeah.
Not only for people to hear you, but as these things are recorded, it's useful to have them on tape.
That is the way IceCube observatory work?
Oh, no. So IceCube, yeah, so good. So the detection physics is similar in the sense that they also look for Cherenkov radiation. So the idea is the same. Again, the neutrino does nothing, but every time you produce a charged particle that's moving with a lot of energy, it will produce Cherenkov radiation. Now, for IceCube, their poster child particle is the muon. So they're very, very good at seeing muons because the muons have a very, very long track, and they can reconstruct the track really well using Cherenkov radiation. Depending on the neutrino energy, they also have something to say about electron neutrinos and tau neutrinos. And we can talk about that in some other discussion. I probably won't talk about IceCube at all. I think Pedro Holanda will talk about IceCube in some context. But yeah, the physics is very similar. The geometry and the size of the experiment are qualitatively different. So IceCube is gigantic. And in order for them to see anything, they need these signals to be really big. And again, really big is the event has to be the size of this room. And again, the way to think about that is they have a lot of photon detectors, but the photon detectors are in these very, very long strings. And the separation of the detectors are in 10 meters or something like that. So that means that in this room there would be like 6 or 7 IceCube detectors. So they are a very coarse experiment. So what this means in practice is that they only measure very, very high energy events. So again, the super K, the atmospheric neutrinos are about a GeV. For IceCube, the lowest energy neutrinos they can talk about are like 10 GeV. They really like 100 GeV and above, and they are really designed to see things with 1,000 GeV or 1,000,000 GeV. Or yeah, so that's they like the PeV stuff, not the GeV stuff. That's a factor of 1,000,000 higher in energy.
Sorry, just.
I'm not, but I could if people ask. But that becomes a long story, a longer story.
Could you repeat the question, just for?
I asked about the neutrino detection from the Blazar that was announced.
I mean, I can talk about it for 5 minutes if people want, just to say what happened. But we can also do it later.
Yeah, it's a good discussion, good question to keep to some point if we lack more.
Is it possible to measure a background of neutrinos produced in every star of the universe, for example? It's cannot interfere in the experiment of polar experiments.
That's yeah. So there are different. So the one background. So he was asking about neutrinos produced in astrophysical objects in the universe, and the one that we're most sure about are neutrinos produced in supernova explosions. And one thing that's interesting is that they're very hard to detect unless the supernova happens very nearby, except that there have been many supernova explosions in the past. So those neutrinos are everywhere, and we haven't been able to detect them yet. And the reason for this is their energies are very low. Their energies are kind of like these solar neutrino energies. Maybe they go up to about, say, 20 MeV or so, but it's still in the solar neutrino territory. And the only reason this experiment can see the solar neutrinos is because they know where the sun is. So if you're looking for something diffuse, it becomes very hard. Now, people have come up with some schemes that allow you to see antineutrinos produced in all the supernova explosions in the past. And the trick for doing that is the same as the trick for observing the neutrinos from nuclear reactors. But the idea is you have to find a way to see these neutrons when the antineutrino hits something in the water. Okay, and people are, right now, they're taking the Super Kamioka experiment. They're mixing something into the detector, gadolinium actually. And they want to do that because that enhances the cross-section for detecting neutrons. And that way they can enhance the efficiency for seeing antineutrinos in this 10 MeV range, with the hopes of seeing the neutrinos produced in the supernovae a long, long time ago that permeate the entire universe. There's a separate thing that Pedro will definitely talk about, which is we also have the neutrinos produced in the Big Bang. So if you believe in cosmology, which we all do, then a lot of neutrinos were produced in the early universe. And those neutrinos...
I don't believe in cosmology.
Okay, there you go. Everybody else does, because they don't know better.
I think nobody believes. I think we have sound proof, and at the best of our knowledge, we're convinced that it's the best explanation. I wouldn't use the word believe. That's
okay, no, I mean, to be more serious, we do have very strong indirect evidence that there are neutrinos produced in the Big Bang. If they are not there, the large-scale structure surveys those data don't work. So we know that there are these neutrinos produced in the early universe. We know a lot about what their properties should be, but we've never been able to see them because their energies are so small that not only are the cross-sections for detecting them very small, they lead to no observable effect. Right? You know, if you have a micro electron volt neutrino hitting something,